So this picture summarizes everything that goes on in a building. We have people, the people are releasing heat, we are releasing heat, so those are internal gains. And we are receiving heat from solar radiation. Okay, so we have this big arrow, and this is the energy from the sun. That's perfect because that energy is for free. Okay, so we have to keep that in mind, that we might have this energy from free for the sun. But then at the same time, if we are in winter, it's cold outside, we have 20 Fahrenheit, we have 70 Fahrenheit inside, and we are losing this arrow, means that we are losing heat through the walls, roofs, windows, and floors. And then we have the ventilation loads. If we don't have the heat recovery, we have the ventilation loads, but even with the heat recovery, we have ventilation heating loads. So we have to supply energy. At the end, that's the energy that we have to supply. If the energy that we are gaining through the sun and because of people is less than the energy that we are losing, then we have to supply some heating. So that's the summary of what happens in winter. We have to keep this guy in comfort at 70 Fahrenheit. And if we don't have enough gains, internal gains or external gains through the solar radiation, then we have to supply some heat. So this is the summary. What have we done so far? Well, so far we have learned how to calculate the heating loads, the energy that we are losing through the wall, through the roof, windows and floors or basements. And we have learned how to calculate the energy that we are losing through the ventilation system. We can have a heat recovery or without a heat recovery, but now we can give a number to the energy that we are losing because of the ventilation. But we haven't done this yet. So we have not worked with the free solar gains that we can have in buildings. And that's important. It's important because there are some days in which our building can be a zero energy building without doing anything, without using PV panels or solar collectors or whatever. If the building is good enough, and even if it's cold outside, but we have a sunny day, we can have a zero energy building because this big arrow or this arrow is bigger than the arrows that are going out. So this is what we're going to try to understand today, how we can calculate heat gains, solar heat gains or free solar gains, because that's for free. We have a window, the window it's well oriented, we have sun outside, and the sun, a lot of energy, enters the building. And how can we do it? With a wonderful tool that the Department of Energy of the United States has developed for us. And the tool is PV watts, PV watts calculator. Okay, there you go. So here we have exciting. Okay, this is it. It's a national laboratory of the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy. Good. Okay, so that is a reliable source because it comes from the Department of Energy of the United States. So can we rely on the Department of Energy? Can we rely on the United States government? Hopefully. Hopefully, yeah. Anyway, in terms of energy efficiency, I would rely on this. So that's what we're going to use. It's pretty easy, and it's and we can use this not just for the school, it's for free for sure. You don't have to register, so you can use it anytime. And even professionals use this kind of, because if you submit your data or your report referring to the Department of Energy tool of the United States, people trust that tool. How does it work? Very easy. First, to get started, we have to type the location. If we are working in Hartford, Connecticut, then you go, and we are here. We are in Hartford, Connecticut. Okay, we have a map. Here we have the coordinates. And this is the solar resource data site. So that means that within 0.7 miles, we have a weather station. So the data that we are getting at this specific location comes from a weather station that is 7 miles away from Hartford. So again, we can rely this. And then we can go to the system. And if we go to the system, here we have a lot of information that we don't need so far. We have information about the PV array. So here we have the DC system size. We're not going to use it. The module type is the PV module that we are using. So far, we're not going to use it. The array type, the same, and the system losses. We are not going to use these 1, 2, 3, 4 fields for this exercise. We will use it in a few weeks. We will be calculating the amount of solar panels that we need, and we will be using this. But so far, we just need information about the solar energy that we get in the building. And we need these two parameters. We need the tilt. The tilt is the angle of the element that we are going to analyze with the horizontal. If it's 20, that means that if this is the horizontal, this angle is 20, so this is 20. And we are going to use this tool to analyze the solar radiation that we have on a window. So if a window is a vertical window, if the window is vertical, then this angle is 90. Okay, so first thing we have to type, because we are using this now, today, to analyze windows. So this is 90. And then the azimuth is the angle with respect to the south or north. It depends. We have a line that is the north-south line, and then there's another line that is the east and west. Okay, so if our building is here, if I open a window here, this window is south oriented. So what's the angle that I have to type here? You have to click on this I information. And here we have the angles. Okay, so they have these criteria. North is 0 and south is 180. So by default, we have 180. So we are analyzing southern windows. The tilt is the angle. So it's vertical, at 90. The azimuth is the angle depending on the north sign or the north arrow. So by the, well, here we have information. If it's we're analyzing in the east facade, we have to type 90. If we're analyzing west, we have to type 270. But if it's south, it's 180. So let's make this example with the southern windows in our file. Okay, so you see that here we have windows. This is the area of the south, the area of the west, the area of the north, east, and then the total area. I'm going to insert arrows a few of them, and then I'm going to copy the format here. Okay, so this is the southern windows, that's the area of the southern windows, and this is the U value of the southern windows. We might need another value here, which is the solar heat gain coefficient. The solar heat gain coefficient of the window. And I'm going to type here something. What is the solar heat gain coefficient of a window? let's. The solar heat gain coefficient is the fraction of solar radiation admitted through a window, door, or skylight. Okay, so it's the amount of solar radiation that enters the building. We have a solar radiation outdoors, and then we have a window. So this window is transparent, kind of, but even a transparent window like this admits only like 80% of the solar radiation. If we have sunglasses, the solar heat gain coefficient of sunglasses, it might be 0.2 or 3, only 20 or 30% of the solar radiation goes beyond and gets to your eyes. So in buildings, we can have this kind of tinted glass. Okay. So sometimes we tend to think that the glass is transparent, but it's not. Okay, so if we see especially office buildings with a huge glass area, and they're almost very dark gray, so that means that the solar heat gain coefficient is very low because basically the glass is not transparent. Sometimes we have this mirror effect. If it's a mirror, that means that it's reflecting a lot of light, and that light that reflects doesn't get into the building. Okay, so when we have glasses like this that have colors, or they look like mirrors, or they are so this is coming from outside. So basically, this is not transparent. Okay, so if it's not transparent, means that the sunlight is not entering the building. So that's and we have examples like this, especially in office buildings, a lot. Okay. From inside, we can see the transparency, but from the outside, we don't see this transparency. And we can have different colors. So the color, the reflection, it affects the solar heat gain coefficient. So when we have a transparent glass like this, the solar heat gain coefficient is around 0.7, 0.8. So only 70 or 80% of the solar radiation enters the building. If we have glasses like this, like mirrors, the solar heat gain coefficient can be 0.2, 0.3, only 20 or 30% of the light enters the building. Okay, so we have to keep that in mind. And in this Excel file, now we have a field here with the solar heat gain coefficient. So if it's 80%, if it's quite high, we can type 0.8. This solar heat gain coefficient goes from 0 to 1. 0 is something okay, it's not transparent. 1 means that it's 100% transparent. No glass, it's 100% transparent. Okay, so it can be 0.9, 0.95, but we hardly ever have 1 as a solar heat gain coefficient. So for these glasses that we're used to, we have like 0.8, 0.75, 0.8, something like that. Okay, so we need the U value and we need this. Where do we get this information? If we have a solar heat gain coefficient catalog. So we have to go to the glass manufacturer, and here this side can be reached. Glass brochure. Okay, so we will get this information from the glass manufacturer. And first we have all the wonderful things they can do. But what we are interested in is in the charts that eventually we will have somewhere. Okay, this is it. Okay, so at the end of these fancy pictures, this is what really matters. So when we have a glass manufacturer, here we have the U value and the solar heat gain coefficient. Okay, So this is what really matters. What do we? Okay, yes, it's very beautiful. Yeah, you can do this. Okay, but give me information about your class. This is the information of the value and the solar heat gain coefficient. So here the U value is 5.8. Be careful with the units. Solar heat gain coefficient doesn't have any units, it's just a percentage. So we don't have to convert those units, but you see that this is pretty clear. It's 0.1, 0.9. This is transparent, and we are going to 0.8, 0.7, 0.6. Okay, so we are reducing the transparency as we are lowering this number, 0.56, 0.47, whatever. But this is the information, and this is 0.36. This is the information that we get from this kind of catalogs. Okay, so we have the solar heat gain coefficient and the U value. And we don't have to calculate anything. We have to go over those catalogs, and then we can select the material that it's better for our buildings. But this is it. Okay. So let's type here 0.8, and but we can look at this. We can select. So there are thousands of options, and now this is 0.13. Okay, so this 0.13 means that it's almost opaque. Only 13% of the sunlight enters the building, so it's almost a mirror. So once we have decided in this catalog what kind of glass we are using, we type here the U value, we type here the solar heat gain coefficient, and then the area. The area is the area of our building, of our south facade. Okay, but we were working with the PV watts. Okay, so with the PV watts, we're analyzing a window. It's south oriented because it's 180. The window, it's a vertical window. If it were a horizontal skylight, this angle would be 0, but 90, it's a vertical window. So let's go here, let's go. And this, here we have two columns. Well, we have three columns, the mount, the solar radiation, and the AC energy. AC energy is the energy that if this were a PV panel, that's the energy that the PV panel would be delivering. But again, we're not analyzing PV panels yet. So the solar radiation, the values that we need are these, the solar radiation. So this is the solar radiation that gets to the element. It can be a solar panel, it can be a window. Okay, so that's the solar radiation that we have outside the building. So the solar radiation that we have at the other side of the building. So how can I explain this? If there's a wall here, and we have a window there, so the window can be light blue, and this is a wall. Okay. Now we have the sun. So this big yellow arrow is the sun. So actually, this is the solar radiation that we have in PV watts. Then we have a solar heat gain coefficient in this window. Okay, so the solar heat gain coefficient is like a shield that blocks part of this solar radiation. So the energy that we actually have inside our building is less. If the solar heat gain coefficient is very high, this arrow inside is almost as big as this one.
If this solar heat gain coefficient is very low, then this arrow it's much smaller. Okay, but that's the idea of the solar heat gain coefficient. So what do I need to understand now? We have this here. Okay, so we have the yellow sun rays outside the building, and then part of this solar radiation enters the building. That depends on the solar heat gain coefficient that we have in this window. Okay, so we need to calculate this value, and this is what PV watts. Okay, so that's the value that comes from PV watts. And that's the value of the solar heat gains inside the building. Okay, so this is what we have to calculate, and this is what we get from PV watts. Okay, so this is PV watts. So in PV watts, we have different numbers for different months. So this is the total, this is the daily radiation. So those are kilowatt hours per square meter per day. So that's what happens on a day in January, in February, in March. So it's an average. We can have cloudy days in January, or we can have sunny days. But the average is 3.9 kilowatt hours per square meter. So this is energy per area. We have to turn these units into BTU per square feet to be consistent with with our Excel file. But these values are important. So if we're analyzing this in January for the heating loads, or in December, this is the extra heat that we get from the sun, the free heat that we get from the sun. But we have this outside the window. Then we have solar heat gain coefficient. We filter part of this energy, and that's the energy that we end up having. So that's what we are going to analyze right now. The first thing that is like weird. This value is higher in January than in July. Why do we have more solar radiation in January than in July?
Because we're closer to the sun.
Hmm?
More sunny, or because we're closer to the sun in orbit, or more solar rays.
So we have more solar radiation in January because the sun rays are almost perpendicular to the wall, because I have done this for a perpendicular wall. If I change this angle, okay, so if now the angle is 0, 0 means that it's a horizontal surface, and I don't change the azimuth. If I go here, now we can see how the solar radiation in July it's much more than the solar radiation in January or November or December. Okay, so we have more sun in summer. Days are longer in summer, so we have more solar radiation. But on a vertical surface, in winter, we have more solar radiation than in summer, which is perfect for us. So nature is helping architects, because what we need in winter is to make the most of the sun. So in winter, we have vertical windows, and we have a lot of sun entering the building. In summer, we have vertical windows, the sun is very high, so the amount of sun entering the building is less. And that's what we want. We don't want sun inside the building in summer. We want sun inside the building in winter. So be aware of that. Anyway, we are in a vertical window, so the angle is 90, the azimuth is 180, that means that we are in the south. And these are the numbers that we get. And we get more solar radiation in January than in June, July. Okay, so now we have to add all this information into our Excel file. So I'm going to type here, January. Is Revit smart enough to understand that this is February? Revit is amazing. February, March, April, May, Revit, Excel file, I mean Excel. June, July, August, September, October, November, December. Okay, so we have here all the months from January to December. And here, this is the month. So what do we get from PV watts? We get these units: kilowatt, meter square, day. So I'm going to type this here: kilowatt meter square per day. Okay. What's wrong with this? Since we're using the imperial units, that would be BTU. It's kilowatt hours, so that would be BTU. That's the energy unit per square feet per day. Okay, so we have to turn kilowatt hours to BTU, kilowatt per square meter to BTU per square feet. And how can we do that? We have to convert. So we have to go from kilowatt hour divided by square meter to BTU per square feet. And it's 317, it's 316.99. Okay, so it's 317. So what I have to do is to multiply 1 kilowatt hour per square meter times 317. So that number, first, yeah, so that's, I have to type here the values that I get from PV watts. Where's PV watts? Okay, I have to type these values here. So this is 3.9, 4.16, 3.83, 3.26, 2.71, 2.53, 2.68, 3.13, 3.9, 3.8, 3.69, and in December 3.2. Okay, so we need to get this data. So this is the solar radiation outdoors on a vertical surface, on a vertical window. And we have to get this data throughout the year. Now I have to turn this into BTU. So this cell equals the value in kilowatt hours times 317. And now I can go all the way here. Okay, so this value 1236. This is the value that I get BTU per feet square. This is the value that I get here. Okay, this is the solar radiation outdoors that gets to my glass here. Now, if the solar heat gain coefficient is 0.8, if the solar heat gain coefficient is 0.8, so what's the value of this arrow? So it's 1, 2, 3, 6 times 0.8. So this is 988. $988. Okay, how can we do that in our Excel file? Here, we multiply this equals, it's this times the solar heat gain coefficient. So I have to click on this cell. And this is 989. What if I drag this here? I don't get valid values because here I'm taking this cell. How can I fix it? By typing here $, because I want the solar heat gain coefficient to be a fixed value. So this is $, and $. Now, if I drag all this, whoops, I get valid values for January, February, March, April, whatever. Okay. I have to insert one row or two more because this is the a solar. Well, this is outdoors, and this is indoors. Okay, because if I multiply this by the solar heat gain coefficient, the solar heat gain coefficient doesn't have any units, doesn't have units, it's just a number from 0 to 1. So the units are the same here, but this is outdoors and this is indoors. And finally, I have to multiply this by the area of the windows, okay? Because what's the energy? This is per square feet, so I need to multiply this times the area of the windows. So I can type equals this one times the area of the windows, and I'm going to type $, because I want to drag this. And I need to have all the numbers with the same. And what are the units here? This is BTU per day. So I cancel square feet. So this is BTU per day. Okay. So that's the. So I'm going to do it again. Well, do it again. I'm going to explain it again. These values, I get these values from the PV watts. So just have to type these values. It's only 12. It's not a big deal. Then I have to multiply this. Well, I have to convert units. Here I'm converting units from kilowatt hours to BTU. Then here I'm multiplying this times the solar heat gain coefficient. So that's the difference between the outdoors solar radiation and the indoor solar radiation. And finally, here I multiply times the area of the windows, and make sure that we always have this cell multiplied by the area of the windows here. And the units are BTU per day. What would I do here? I need the thermal loads, but the thermal loads in the southern windows. Okay, so what's the thermal load of the southern window? We have not this, so I have to fix this. First, I have the U value of the window, this one. Second, I have the area of the window, that one. And this is indoor minus outdoor temperature. Okay, so this is the thermal loads, and this is the south windows. But now I have to compare apples and apples, pears and pears, melons and melons. So I have to compare the right units, because these are BTU, and these are BTU hours. Okay, so let's do it. We're doing this exercise in winter. So what I need is in January. Okay, so that's the energy that we get in January. It's a huge number. It's 213,000. $213,632. 632. This is BTU day, because we are dealing with energy. Okay, so that's daily energy in January. That's the daily energy in January. So what is the heat loss? The heat loss that we have on one day in January, well, one day we have at this specific moment, it's the power that we have here. So it's 8,985. 8,985 units, BTU divided by hour. What's the daily energy loss? The daily energy loss is 8,985. And now we have to multiply this by times, because here we have BTU, and here we have BTU divided by hour. So how many hours do we have in one day?
24.
24, yes. If things don't change, we have 24 hours a day. So now what's the daily energy loss through this window? Because there is another arrow here. So we have an arrow that it's going outwards. And this is a red arrow. Okay, so we have energy gains due to the sun, but we have energy losses due to the window. So what's this daily energy? That daily energy is, calculator, 8985 times 24. So it's 215, no, 215,000 640 units BTU per day. Okay, so now I can compare this because here I have BTU per day. And here I have BTU per day. This is BTU per feet square. I have to multiply this times the feet square. So that arrow is this number. And this is BTU. This is 988, it's BTU per square feet times the square footage. And now we have this BTU. And the number here is 215,640.
Okay, so that's interesting because I have this window. In January, it's very cold outside. We have 20 Fahrenheit outside. And we have a lot of heat losses because we are losing, this is 72 Fahrenheit minus 22. Okay, so I'm losing 215,000, but I'm gaining 213,000, so almost the same. So I'm opening a window to the south. It's great. Now let's work with the mirror. Okay, if I had a northern window, this is the south. This is it, and this is the north. So in the northern window, I have the same glass with the same solar heat gain coefficient. That's perfect, but this arrow doesn't exist. This arrow doesn't exist. And these gains, we don't have it. We don't have these gains. We don't have these gains. All this belongs to this. Okay, and this arrow, it's in the other direction. Okay, so this is the south, and this is the north. In the south, everything works well because we are losing the same energy that we are gaining. In the north, we are losing all the energy. We are not gaining anything because we don't have sun. So what do you have to do? Reduce the size of the northern window. And then we will reduce this arrow. Okay, so that's the goal here. We have a huge window to the south because we have a lot of heat gains. We do have heat losses, but we do have heat gains. In the north, if we need windows, because we do need natural light, we have to minimize the area because we only have losses. We don't have any gains in the northern windows. And we have done this with 24 hours. In this building, the building is not open 24 hours. It's open probably from 8 a.m. to 8 p.m. So this is only 12 hours. So if we do this with 12 hours, it's not that number. It's 8, 9, 8, 5 times 12. Okay, so this number is 107 now, 107,000. 7,800, whatever. $820. Okay, so now this arrow is smaller because we don't have 24 hours.
Okay, so now we are gaining more energy that we are losing through that window. So again, it's even better. If we don't count 24 hours in this building, we don't have to, why we don't have the heating system on at midnight. If nobody, at least, well, this system is good enough. If there's someone working at midnight in the computer lab, the heating system can be on, but only in the computer lab, not in the whole building. Okay, but this is because of the system. But that's the goal. Opening these windows to the south, it always works, even in cold countries, even in New Hampshire, or even in Alaska, or even in Laponia, in Finland. It's always a good strategy, opening big windows to the south, small windows to the north. In other latitudes, if we were here close to the equator, I wouldn't do that. But if we are in the northern hemisphere, from latitude 40 to above, the goal is always the same. We have to open big windows to the south, small windows to the north. This is what we have here. We have a lot of curtain walls and windows to the south, and we have small windows. Well, they're not that small, but they are not as big as those windows there. So that's the goal of this exercise. The thing is that we have to compare energy and energy. So here, the heating loads or the thermal loads are BTU hours. This is power. But then we need to know, okay, how many hours is our building running? 10 hours, 12 hours, 24 hours. Then we have to multiply all these times the hours per day or per year that the building is working. And then we can compare energy and energy. But we have to do this with all the windows. Okay, we need a table like this with all the windows. With the eastern windows, we have to go to the PV watts. And we can change two things. This is the angle of the windows. It's always 90 because it's vertical windows. If we want to type here east, east is 90 degrees. So I have to type here 90. I go, and this is the solar radiation that we have on, so this one is the solar radiation. So I have to copy this table, but now in these results from PV watts, this is what comes from PV watts. On the east elevation, I have to change these numbers. Okay, so I have to type these numbers again. It's 1.47, 1.9. And then we will have to do the same with the west, and we will have to do the same with the north. Well, even from the north, so what is north? This one, 0. So if the azimuth here is 0, this is a north elevation, and we calculate something, we do have solar radiation. It's point something, 1 point something, but even from the north, we are getting some heat now because, well, natural light has a little amount of heat on it. It's not a direct sun, but even with the north facade, we can get some solar radiation. Very little, 0.5 something. But even with the north, from the north, we can get some heat. Difficult to understand, but with the south, it's very clear because we see the sun. We see the sun entering the building, and we are exposed to the sun, and we heat up when we are exposed to the sun.